Okay, let me do this. All right. Okay, so today the plan is to focus on chapter 3. So I didn't realize until after the fact that I accidentally published the assignment for chapter 3, and some of you actually did it and uploaded it into Canvas. Unfortunately, however, you guys who did it and uploaded it into the same Dropbox for assignment 2. So basically, and in one case I know somebody did both assignments 2 and 3 on the same document. So I'm saying that to say that basically what you need to do is to upload assignment 3 after completion into the Dropbox, which I'm going to create later on for that assignment. All right. I like to keep things in that kind of order, each assignment to their own Dropbox. All right. So with that said, the first thing I have to ask you guys is, do you have any questions concerning the videos for chapter 3? All right. Anything that you need explaining, or any area of difficulty that you might have concerning chapter 3? If not, let me hand these out to you guys. If you have not printed it already, I know some of you may have done that, so. Okay, take one and pass down behind you. Oh. Oh. Okay, so basically I want to go through these questions with you guys. Like I said, I know some of you have answered them already and uploaded it in the Canvas, so this may go more quickly than I had originally planned. And for you guys out there in Zoom, I am going to publish that. Oh, it's already published. I'm sorry. So I'm going to bring it up here. So we can look at it together. And then after we're finished with this, if there's time left, then I'll just basically proceed to chapter 4. Here you go, sir. Okay, so let me. Okay, so the first question has to deal with some terminology as it applies to different substances, right? So the question is asking in number 1, classify as a pure substance, and they put in parentheses here, either element or compound, right? So if it's a pure substance, you have to state whether or not it's an element or compound, or if it's a mixture, and again in parentheses, they put homogeneous and heterogeneous. So in other words, if you're going to say it's a mixture, then you have to state what kind of mixture it is. All right. So let's talk about the air that we breathe. So what's the classification you'd put there? Let me turn on this here. Hold on 1 minute.
Mixture.
It definitely would be a mixture. 1 minute here. Okay, so what kind of mixture would it be? Homogeneous mixture, right? So just to remind you, a homogeneous mixture is one that is uniform mixture. Uniform throughout, all right? So air is a good example of that. In fact, all gaseous mixtures, if you mix any gases, 2 or more gases, the result will be a homogeneous mixture, all right? Okay, what about B, a nickel?
Or substance.
I'm sorry?
Or substance element.
Well, it says a nickel, so it's not talking about the element itself. I think it's talking about the coin.
Or substance.
I'm sorry?
Is it pure substance?
Is it?
Pure substance?
No, not a pure substance. It would be a mixture.
Oh.
Right. So the question now becomes, what kind of mixture is it?
Nickels mixed with other metals, wouldn't it also be homogeneous?
Exactly. So homogeneous mixture. All right. Mixture of metals, they're known as alloys. I don't know if you've ever met that term before, right? Alloys are metals that are mixed together, like brass. What's the other one? Well, I would say steel, accepting that steel is a mixture of iron and carbon. But brass is an example. I'm sorry? Bronze is another example. Yes, thank you. Okay, so those are examples of alloys, which are homogeneous mixtures. Okay, the next one is magnesium.
Pure substance.
It's a pure substance, and is it an element or compound? Okay, so pure substance, element. All right. Okay, seawater.
It's a mixture.
It's a, you said hetero?
It's a bunch of salt in it, right?
It has salt and other substances in it. I'm thinking that if we assume that it's seawater without any, like particles, sand and so on. So in that case, it would be a homogeneous mixture. All right. And then we get to gasoline. It's a mixture. And what kind of mixture is it?
Homogeneous.
I'm sorry? Homogeneous, exactly. Gasoline is actually a mixture of a group of compounds known as hydrocarbons, right? Hydrocarbons are basically compounds, organic compounds, which contain carbon and hydrogen only, right? And you have different blends, so to speak, for gasoline, for diesel, and other uses, right? So that's a homogeneous mixture, gasoline. All right, so much for number 1. Let me clear this here and move on to number 2, which says label each of the following as either a physical process or change, or a chemical process or change. So just to remind you, a physical process or change is a change where there's no change in the composition or structure of the substance, right? So to use an example that is not here in this list, water, H2O liquid, you can cool it to a low enough temperature that it becomes solid, right? So that would be an example of a physical change, right? Because you're not changing the composition of water when you cool it from the liquid state to the solid state, right? It's still H2O, all right? Another example would be the vaporization of liquid water to gas, right? Again, that's another example of a physical change. An example of a chemical change would be, for example, starting again with water. If you pass an electric current through water and it breaks up into its constituent elements, hydrogen and oxygen, right? That is called electrolysis, right? That's an example of a chemical process because you're starting with one substance, water, right? And then by the process of electrolysis, you're creating different substances, hydrogen and oxygen, all right? So those are just some examples of physical and chemical changes. So with that said, let's look at number 2A. The metal gets warmer. So what type of
Physical?
That would be physical. Yes, sir. Yes, ma'am. Okay, the next one is explosion of nitroglycerin. Chemical. Any kind of explosion is a chemical change. Corrosion of iron metal. Chemical, right? And then water condenses on the metal. Physical. Exactly. All right. Okay, very good. So that's relatively easy. Let's move on to question number 3, which says, identify the characteristics, the following characteristics as physical properties or chemical properties. So again, it's kind of related to what we discussed before, but this time we're talking about properties. Simply put, when we talk about the properties of a substance, we're talking about those characteristics that are associated with that particular substance. So things like melting point, boiling point, color, and so on, right? And those are physical. Chemical properties are basically the type of chemical changes that a substance would undergo, all right? So that's basically the difference between the two. So let's start off with iron forms rust on exposure to air and moisture. So is that a chemical or physical property? Chemical, right, because basically that's a chemical reaction where the iron is converted to rust, which is iron 3 oxide. So that's an example of a chemical property. Zinc has a density of 7.13 gram per mil at 25 degrees Celsius. Physical. Silver is a lustrous metal. Lustrous basically means shiny. That would be also physical. And zinc dissolves in dilute hydrochloric acid, producing hydrogen gas. Chemical, because that's basically describing a chemical reaction that zinc would undergo. Here you go, sir. Okay, so far so good. Scrolling down. Okay, so basically, again, we're looking at chemical or physical properties. So basically, this question is asking for you to identify. Here you go, sir. Identify the following as either chemical or physical properties. So basically put C for chemical and P for physical. So let's start off with number 1. If something has a color blue, that would be physical. So we're going to put P here. Density, physical. Flammability, which means burn, chemical. Any burning involves a chemical reaction. Solubility, physical. And this is true in most cases. There are some cases where it could be chemical, but for now, we're just going to accept that as physical. Reacts with acid, chemical. Supports combustion. I'm sorry? Chemical. Sour taste, physical. Melting point, physical. Reacts with water, chemical. Hardness, physical. Boiling point, luster, physical. Odor, and reacts with air. Okay, very good.
What is luster?
Shiny again. Yeah. Okay. Can I clear this? All right, let me scroll down. Okay, so again, physical and chemical. This time we're looking at changes. Okay, so let's start with sodium chloride dissolves in water.
Physical.
Physical. Silver tarnishes. Chemical. An apple is cut. Physical. Heat changes water to steam. I'm sorry? Physical. Baking soda reacts to vinegar. Chemical. Iron rusts. Chemical. Alcohol evaporates. Physical. Okay, I need to clear this and scroll down. Ice melts. Physical. So that would be P. All right, so that's that. And then we have to go to the other side. You know what? Let me make this a bit smaller. Oops. this work. Okay, so on the other side, we have milk sours. Are we chemical? Sugar dissolves in water, physical. Wood rots, chemical. Pancakes cook, chemical. Grass grows,
Chemical.
chemical. A tire is inflated, physical. And I think, scroll up here. Oh, we have some more here. Let me clear this. Okay, so
Food is dissolved.
food is digested,
Nitrogen.
chemical, and paper towel absorbs water, physical. Okay. All right, so let's clear that. And let's go down. Okay, so it says here, can you recognize the chemical and physical changes that happen all around us? If you change the way something looks, but you have not made a new substance, then that would be a physical change. That's what we talked about earlier, right? No change in the composition or structure, right? However, if there's a change in the composition or structure where you create new substances, then that would be a chemical change. Okay, so let's look at what we have here. Starting with an ice cube is placed in the sun. Later, there's a puddle of water. Later, still the puddle is gone. So, exactly. All that we have described here would be physical changes, all right? Okay, the next one, number 2. 2 chemicals are mixed together and a gas is produced. Chemical. Okay, a bicycle changes color as it rusts. Chemical. A solid is crushed to a powder. Physical. 2 substances are mixed and light is produced. That would be chemical. Okay, a piece of ice melts and reacts with sodium. Well, there are 2 changes. Firstly, the ice melts, which is what? Physical. And then when it reacts with sodium, chemical. All right, so that's a combination right here. Okay, number 7, mixing salt and pepper. Physical. Chocolate syrup dissolved in milk. Physical. A marshmallow is toasted over a campfire. Chemical. And then let me clear this, see if there's anything more down here. Marshmallow is cut in half. Physical. Okay, very good. All right. So let's scroll down now to number 7. Now in number 7, it says, classify each of the following as elements, E, compounds, C, or mixtures, M, and then write the letter X if none of the above applies, all right? So those are the options, E for elements, C for compounds, and M for mixtures, all right? So let's start off with this line, this row right here. Diamond, element, because it's a form of carbon. Sugar, compound. Milk, mixture. Iron, element. Okay. Air, mixture. Sulfuric acid, compound. Gasoline, mixture. We saw that earlier. Electricity, none of the above, right? It's actually a form of energy, so we put X there. Krypton, element. Bismuth, element. Uranium, element. Popcorn, mixture. Water, compound. Alcohol, compound. A pail of garbage, mixture. A dog, mixture. Ammonia, compound. Salt, energy.
Compound.
Nope, none of the above, right? Gold. Element, okay. Wood, mixture. Bronze, mixture. Ink, mixture. And pizza. I just had pizza for dinner yesterday.
Why wouldn't bronze be a compound?
No, bronze would be a mixture because it's a mixture of two metals. Yeah. Okay, let's see here. Oh, there are more. Okay, so let me clear this here. Okay, so dry ice, compound, baking soda, titanium, and concrete. Okay, very good. All right, so here it is. Okay, so this question gives you some model representation of different molecules and atoms and so on in different situations, different types of mixtures. And it says match each diagram with its correct description. So they gave you the descriptions down here. And you are to tell, match each of them with each of these as you observe it, all right? So number one is pure element, which means that there's only one type of compound present. So that would be C, I would agree with you there. Two, mixture of two elements. Two types of uncombined atoms present. I'm sorry? E, exactly. Oops, E. And then a pure compound. Only one type of compound present. B. A mixture of two compounds. Two types of compounds present. A. And then a mixture of a compound and an element, which would be by default D. All right. And that's it. Okay, let's see here. Oh, and that's it. Okay, so we're basically finished with that assignment. So what I'm going to do right now is create a Dropbox for it. Let me do this, 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 and then let me go here. Okay, so assignment number 3. Okay. Oops. Okay, so I'm going to set a deadline for Monday for the completion of that assignment. Oh, shoot. Okay, and let me save this. Okay, so now the Dropbox is available. Make sure that you submit your assignment by midnight on the 26th, which is Monday. All right. And let me just say, and this is based on, I'm in the middle of grading assignment. Did I give you guys back assignment 1? I did? Okay, good. I'm in the middle of grading assignment number 2. And let me just say that, and I've actually made some notations on particular assignments because some of you, a good portion of you, have done the assignment on, not on the original document itself, but on a separate sheet of paper. I will accept it for now, but for future reference, make sure that you complete the assignment on the original handout, all right? You can do that in pen, black or blue ink, or if you have the capability of actually doing it in your own handwriting, on a particular device, iPad or whatever, then I'll accept that as well, all right? Which brings me to the other issue I've noticed. Some of you, not many of you, maybe 1 or 2 of you, have submitted your work typewritten. I will not be accepting that anymore. I'll again, grade it as it is for now, but make sure that you complete your assignment in your own handwriting. Again, blue or black ink pen, or if you have a device that you can write on, I will accept that as well. All right. So that's it as far as this assignment is concerned. So what I'm going to do now is proceed to at least get you guys started off on chapter 4. Of course, I've posted. In fact, let me do this. Let me I just published the PowerPoints, but let me go to the modules. I published the videos for chapter 4. Okay, so that's chapter 4. All right, good. So let me go to the PowerPoint. All right, so chapter 4 deals with the topics you see there on the screen: elements, atoms, and ions. All right. So I think we talked about elements already, but it doesn't hurt for us to remind ourselves of what we mean by that term. An element is a substance which cannot be broken down into simpler substances by chemical means. All right. And these last 2 words are very important, because you can actually break down elements into simpler substances, but that would not be a chemical reaction. That would be a nuclear reaction. All right. You can actually break down, for example, any element like carbon, for example. You can break it down into smaller fragments, which would be different elements. All right. And for those of you who have to do general chemistry 2, then you're going to basically encounter a whole chapter on nuclear chemistry where that will be discussed. All right. So that's very important. The last 2 words right here. An element is a fundamental elementary substance that cannot be broken down into simpler substances by chemical means. So some general information here: all known elements or all known substances are the combination of more than 100 elements, and each element has a unique number. I'm going to say more about that number later on, but the simplest element is hydrogen, and its number is 1. All right. And then you have the other elements that are numbered in order of increasing complexity, right? Now, most substances can be broken down into 2 or more simpler substances by chemical means, right? And these are compounds. And one example of this would be water, which I described earlier. You can pass an electric current through it. We call that electrolysis, and that breaks down water into its constituent elements, right? And if you actually do that experiment, what you'll find is that the hydrogen and oxygen that is produced would be a 2-to-1 ratio, which reflects the same ratio of the elements in the formula, right? The formula for water is H2O, and then when you break it down and collect the gases, provided that the conditions are the same, if you look at the volumes, the volume of hydrogen will be twice that of oxygen, all right? Another example is table salt, right? You can actually decompose, again, using electrolysis, table salt, which is sodium chloride, into its constituent elements, all right? So those are examples of substances that can be decomposed into 2 or more substances, right? So that's the difference between an element and a compound, right? An element cannot be broken down into simpler substances by chemical means, but a compound can be broken down into simpler substances by chemical means. Again, some general information about the distribution of elements. Elements are not distributed equally by nature, right? Oxygen, for example, is the most abundant element in the human body, about 65%, but it is about 49.2% of the crust of the earth. The most abundant element in the universe is actually hydrogen. And then the second most abundant element in the universe is helium. And look at the big difference here, 91% for hydrogen compared to 8.75% in the case of helium. So as you can imagine, the other elements would be less in terms of their percentage abundance. So this is just some pie charts giving you some data information concerning the relative proportions of the different elements under different situations. This is for the universe. As we said before, hydrogen is 91%, and then helium is 8.75%. And then this little sliver right here is where other elements would occupy, which would be 0.25%, all right? Then in this case here, in terms of the Earth's crust, As we said before, oxygen is 49.2%. And then the next abundant element is silicon. Then you have 7.5% for aluminum, and then 4.7% for iron, and then you have the others right here. All right. And then as far as in the human body is concerned, as we said before, 65% of the human body will be oxygen, and then we have the other elements, carbon and hydrogen, and so on. All right. So that's basically showing you how the elements are distributed in different situations. Now, as far as the names of the elements are concerned, the name comes from different sources, right? In some instances, the name comes from a Greek origin, right? So, for example, iodine comes from a Greek word ios, meaning violet, because that's actually the color of iodine. In some cases, it's Latin, the origin that is. So, in the case of, for example, fluorine, it comes from the Latin word fluor. I don't know if that's the correct way of pronouncing it, but basically, that comes from a compound known as fluorspar, which is low melting, right? So basically, if the temperature is high but not significantly high, it melts, becomes a liquid, and it flows. So that's where that particular name, fluorine, comes from. And then in some cases, the origin is Greek, such as bismuth. And this I'm not too clear about, to be perfectly honest. But it comes from the German Weissmass, which means white mass, and then location in some cases. For example, germanium was named after Germany because it was discovered by a German chemist, and in some cases it's named after some elements are named after famous scientists, such as Einsteinium, which is named for Albert Einstein. So, basically the names of these different elements come from these kind of different origins, right? As far as the symbols of the elements are concerned, there are two types of symbols. Well, firstly, let me just say that the symbol can stand for the element itself. It can also represent one atom of an element, especially if you're writing down balance equations, which we're going to talk about later on. And also can represent a particular quantity of the element, again, as it relates to representing the element in a balanced equation, right? Now, the elements, the symbols, I should say, themselves, are two types. You can have either one letter representing a particular element, and that letter is an uppercase letter, or you can have two letters where the first letter is uppercase and the second letter is lowercase, right? So if the first letter is uppercase, some examples here are the elements or the symbols representing the elements like hydrogen, carbon, nitrogen, oxygen, chlorine, argon, and so on. No, not argon, I'm sorry. Fluorine, phosphorus, silicon, and so on, right? So in those instances, one uppercase letter, right? In other instances where you have two letters, the first one is uppercase, the second one is lowercase, such as neon, barium, and we have some here like aluminum, antimony, argon, and so on, right? So basically, when it comes to the symbols of elements, basically those are two types of symbols, all right? Now, in some cases, and as stated here, most cases, most symbols start with the same letter as the name of the element itself, right? So some examples are given here, like aluminum, iodine, barium, bismuth, boron, bromine, cadmium, and so on, all right? But there are other instances where that is not the case, right? It seems as if in other instances, there's no connection between the name of the element and the symbol that is used to represent the element. And the reason why in most of these cases is because the original name of the element is in some other language, which is reflected in the symbol that is now used to represent the particular element, all right? So here are some examples, like antimony. The symbol that we use now to represent these elements, or this element, is SB, and that's because its first name or its former name is stibium. And some other examples are given here. For example, potassium, the symbol is K, right? K, you cannot see the connection between K and potassium, and that's because the original name of potassium was kalium, all right? So that's basically how some of these elements, or some of these symbols are used for some elements where you don't see the immediate obvious connection between the name of the element and the symbol, all right? Okay, now there's several ways of categorizing the different elements in, some broad classes, right? One of the ways is that we can put elements in the category of being either metal, non-metal, or metalloids, all right? So let's talk about the difference between metals, non-metals, and metalloids. Let's start off with the metals. So these are the characteristics or the physical properties of metals, right? Metals, for the most part, are solid at room temperature. In fact, there's only one example, or one exception, I should say, of a metal that is not a solid, and that is mercury. Mercury is the only liquid metal that exists as a liquid under normal room temperature conditions, all right? But every other metal exists as a solid, right? Metals are shiny, right? They also are good conductors of heat and electricity. There's no exception to that particular property. And metals are malleable, which means that they can be rolled or hammered into sheets, all right? So those are some characteristics of metals. Another characteristic of metals is that they are ductile. What that means basically is that they can be drawn into wires, and most metals have high melting points. In fact, I would say all of them. I can't think of any, well, no, actually gallium, I think, is one metal. Its melting point is relatively low because if I remember correctly, if you have a piece of gallium in your hand, which I would recommend that you do, it will melt because of the heat coming from your hand, all right? So I think gallium is the only exception to that particular statement. Metals have high densities. That is true for all metals. And some examples of metals would be gold, iron, and lead. And as far as chemical properties of metals are concerned, metals have very little tendency to combine with each other to form compounds. So it's highly unlikely, and I really can't think of any examples of two or more metals reacting to form different products, right? Basically, if you had two metals under pretty much all conditions, they'll simply mix, all right? What else? Oh, metals, they readily combine with non-metals to form ionic compounds. And later on, we're going to talk about the difference of ionic compounds versus molecular compounds, all right? So for example, they can combine with non-metallic elements like sulfur, chlorine, or oxygen, and others, all right? So what you'll find is that in nature, where you have minerals existing, basically they are the result of the reaction between more reactive metals with other elements, which would be non-metals, all right? Continuing our discussion of chemical properties, now there are some metals, in some textbooks they call them noble metals, and that's because they're very unreactive and therefore they will exist in nature in their free state. For example, copper, silver, and gold, all right? So you have some reactives, some metals that are reactive, very reactive, they don't exist in nature by themselves. And in particular, I'm referring to the metals in groups 1A and 2A in the periodic table, to a lesser extent aluminum, right? But pretty much all the metals, especially those in what is called the transition region of the periodic table, which would be, if you look at the periodic table, that would be in the valley between groups 2 and 13, right? So those elements, they tend to exist as noble elements, or noble metals, I should say. Metals can mix with each other to form alloys. We discussed that earlier. So for example, brass is a mixture of copper and zinc, and bronze is a mixture of copper and tin, all right? Now, this is, as I said before, would not be considered to be an alloy because carbon is not a metal, right? But steel is a mixture of carbon and tin. Okay, so that's as far as metals are concerned. As far as non-metals are concerned, in terms of their physical properties, they tend to be dull. In other words, they lack luster. They tend to have relatively low melting points, low densities, and they tend to be poor conductors of heat and electricity. There's one exception to this. I don't know if I have it listed here. No, I don't. So the exception to this point here would be, okay, where is it? Would be carbon in the form of graphite. I hate when this happens. You know what, let me get rid of this here. Let me do this. Okay, so carbon in the form of graphite. All right. That is, excuse me, that is a non-metallic element that is actually a very good conductor of electricity. All right. And I won't go into the reasons why that is, but that's an exception, right? So let me just put here, this is an exception to that particular statement. All right. Okay, continuing. Okay, so that's basically it as far as the physical properties of nonmetals. Now, in terms of those nonmetals that exist in the solid state, there are only 4 of them, believe it or not: carbon, phosphorus, sulfur, and selenium, right? These elements exist in a solid state, and they are non-metallic elements, right? Those are the only 4 non-metallic elements that exist as solids. And then, and iodine. Iodine is a bit different in that it easily sublimes. In other words, if I take a piece of iodine and I heat it very slightly, then it converts to vapor. But normally under room temperature conditions, it exists as a solid. And then as far as liquids are concerned, bromine is the only nonmetal that exists as a liquid. All right. And then as far as gases are concerned, there are several: nitrogen, oxygen, fluorine, chlorine, and the group 8 elements known as the noble elements: helium, neon, argon, krypton, xenon, and radon. These all exist as gases under normal room temperature conditions. Okay, so we talked about metals, we talked about nonmetals. There's a third minor category of elements known as metalloids. And metalloids are so named because they have some properties in common with metals and other properties in common with nonmetals. So metalloids kind of straddle that barrier or boundary between the two. All right. And there are only 7 metalloids that exist. And these are those elements, right? And if I were to choose one example, like for example, silicon, right? Silicon, one thing that silicon has in common with metals is that they are shiny, right? Remember we said that metals tend to be shiny, right? So silicon has that in common with metals. But on the other hand, silicon is not as good a conductor of electricity as metals, right? So that's just one example of how a metalloid behaves. It has some characteristics in common with metals, others in common with nonmetals, all right? And if you were to look at most legitimate periodic table, not the one that we have here, but like this one here, what you'll find is that in addition to the elements in their right positions, you will find that in most periodic tables, there's this dark line, stepwise line here, which basically represents the boundary between metals, which would be to the left of the periodic table, and non-metals, which would be to the right, right? And as you can see clearly, most elements in the periodic table are metals, all right? So metals to the left, with the exception of hydrogen, of course, which is a gas, and non-metals to the right. And what you'll find is that the metalloids that I mentioned earlier would be on the boundary on one side or the other. So you have boron here, silicon here, germanium on the other side here, and so on, right? So that's basically collectively how the periodic table shows you the difference between metals, nonmetals, and metalloids. And this basically shows you which the categories of the different elements, all right? Another thing I want to point out here while I'm at it. So back in the dark ages when I was in high school, the periodic tables that you'll come across back then, would have the group numbers 1A, 2A, right? And then you skip all of this here, and then you have 3A, 4A, 5A, 6A, 7A, and this would be, it's not shown here, but this would be 8A, right? So that was back in the day. And then somewhere between when I graduated high school and when I graduated college, the powers that be decided that they would adopt a different numbering system where you simply number the groups 1, 2, 3, 4, 5, like it is in that periodic table. You'll notice it's just basically a straight numbering system from left to right for the columns, 1, 2, 3, all the way over to 18 on the right side of the table, right? And if you look at different textbooks, you'll see one or the other system be used. Of course, since I was indoctrinated with the old system, I prefer to use the old system, but I mean, the other system is just as useful, all right? But there's a reason why I prefer the old system in that it tells you something about the electronic structure of the atom, the numbers here, all right, the 1A, 2A, and so on, which we'll get into later on. Okay, so this is just reiterating what I said. The metals are found to the left, the non-metals are found to the right, and the metalloids are somewhere in between, all right? Okay, some other terms which we need to, what time is it, man? Okay, some other terms that we need to talk about, atoms, right? Which of course is the smallest particle of an element that can exist, right? And we're going to talk about the nature of atoms, the structure of atoms, and so on. Also, the atom is the smallest unit of an element that can enter into a chemical reaction. So of course, people have been interested in, okay, what is the smallest unit like for any substance, right? Before, and I'm talking like way back in history, you know, the times of the Greeks and so on, I think they had a word. Do I have it here? Right. Oh, no, I don't have it here. So the Greeks have a word for the smallest unit of a particle. And of course, you know, those are ancient times, so they did not have the instrumentation to actually confirm this. But basically, the Greek term is atomos, right? Which is basically the term for the smallest unit of matter. So in their imagination, they're thinking that, okay, if I take, for example, a piece of carbon, and if I had the ability to break it down into its smallest unit, they call it atomos. And that's all they can say. They don't know anything about it, right? And then centuries passed, people were able to do, you know, chemical reactions and so on. And based on the information gleaned from that, an English school teacher by the name of John Dalton proposed a model. It's called the atomic theory. And there are several assumptions of that theory, which we are going to get into right now. As soon as I do this. Okay, so these are the assumptions of the Dalton's atomic theory, all right? And this is one example of how the scientific method works. If you remember, I spent some time the last time talking about, the scientific method. You have your observation, then your hypothesis, and so on. So this is a good example. Our current understanding of the atomic theory has been gleaned or gained as a result of different people coming up with different ideas and doing testing, refinement of their theory, and so on, until you get to an established theory. So based on the information that Dalton had at his disposal, he came up with the following assumptions. The first of which is that elements are composed of minute, indivisible particles called atoms, right? Now, let me just say here, before I even move on to the other assumptions, let me just say that we now know this not to be true, right? Because as I said before, you can actually break down atoms into smaller fragments. In fact, the more fundamental fragments of atoms would be the protons, the electrons, and the neutrons. And we're going to learn more about that later on, all right? So this is an example of a theory that was accepted back then based on the information that they had back then. But of course, with further experimentation, development of technology, which allows us to probe into the nature of the atom, we now know that the first assumption made by Dalton is not true, all right? And that's how science works, of course. Okay, the second assumption is that atoms of the same element are alike in mass and size, which we now know to be generally true. Again, there's some modification to this because of the existence of what are known as isotopes. I don't know if you're familiar with that term, but isotopes are basically different atoms having the same, let me rephrase that, different atoms of the same element, which has different masses, right? So basically, this is not 100% true. Let me put it that way, all right, for the second assumption. For the third assumption, atoms of different elements have different masses and sizes. We all know that to be true. Chemical compounds are formed by the union of two or more. That should be two or more, I should have had here, atoms of different elements, all right? And then number 5, atoms combine to form compounds in simple numerical ratios such as 1 to 1, 2 to 2, 2 to 3, and so on. So for example, H2O, 2 parts hydrogen, 1 part oxygen. Carbon dioxide, 1 part carbon, 2 parts oxygen, and so on. And then atoms of 2 elements may combine in different ratios to form more than one compound. So a good example of this is that you can have hydrogen and oxygen combining to form 2 compounds, one of which would be H2O, which of course we all recognize to be water, and the other one is H2O2, which is hydrogen peroxide. So even though they're made up of the same elements, because the compositions are different, they're different compounds. Okay, let me clear this here. Okay, so actually the example of water I think is being used right here. This is just reiterating the assumptions that we just discussed. Dalton's atoms, according to his theory, are individual particles, right? And they'll look different, right? So atoms of oxygen will look the same if you could see them, and the atoms of hydrogen will look the same. But of course, the atoms of hydrogen and oxygen will have different appearances and different masses and size. All right. So that's what's being shown here. Okay. The other assumption is, okay, what I just said, atoms of different elements have different masses and size. So if you were to see the hydrogen atom and oxygen atom, they'll look different in terms of their masses and their sizes. And this is where I just mentioned the example of water and hydrogen peroxide. As I said before, hydrogen and oxygen can combine to form 2 different types of compounds. One would be water and the other one would be hydrogen peroxide, all right? So in the case of water, there's a 2-to-1 ratio between the hydrogen and oxygen. And in the case of the hydrogen peroxide, it's a 1-to-1 ratio between those 2 same elements. Okay, so let's talk about the composition of compounds, right? And this will be a bit of an introduction, but later on, I think in chapter 6 or 7, we're going to get into a more, a discussion of a more quantitative approach, right? But this is just basically kind of qualitative. The law of definite composition. This is a law which talks about the fact that a compound will always contain 2 or more compound elements, chemically combined in a definite proportion by mass. And I think we're going to use the water example to demonstrate this particular law. So if you look at water in a more detailed way, if you could break down water into its constituent elements and you weigh the hydrogen and the oxygen, what you'll find is that 11.2% would be of the water that is broken down would be hydrogen, and the rest, which is 88.8%, would be the oxygen, right? And that is true for every single sample of water that you will encounter. It doesn't matter where you get it from. It doesn't matter if you get it from the tap, or from a river, or from a sea, or from rainwater. As long as it is water, that would be the composition, all right? And as stated here, if you have a compound and the percentages are different compared to what we have here, then you know that's not water, it's something else, all right? Okay, now hydrogen peroxide is also made up of hydrogen and oxygen. And if you were to break down it into its constituent elements, you'll see that 94.1% is hydrogen, and the 94.1% would be oxygen, and 5.9% of it would be hydrogen. And again, those percentages are fixed for hydrogen peroxide regardless of its source, right? If you get a compound which has different percentages for these elements, then you know that you're not dealing with hydrogen peroxide, right? So that's one law, right? The law of definite proportions. And then there's a law which is known as the law of multiple proportions. And what this law says is that atoms of 2 or more elements may combine in different ratios to produce more than one compound. Now, this you will not find in your textbook, but you still need to know this, all right? So just to give an example of how this law works, let's say we look at 2 compounds, actually the same 2 compounds that we were discussing, right? Water and hydrogen peroxide. So let's say you have a certain amount of each of these compounds where the mass of hydrogen is the same in both cases. And then you compare the mass of the oxygen in both compounds. What you're going to find is that the mass of the oxygen, provided that the mass of the hydrogen is the same, the mass of the oxygen, when you compare these two, for those two compounds, would be in a small whole number ratio. In this case, it would be a 2-to-1 ratio. All right? And that is true for every compound that have different combinations of the same elements, right? If you keep the mass of one of them fixed, then the relative amounts of the other elements would be of a small whole number ratio. So it could be 1-to-1, it could be 2-to-1, 3-to-2, whatever, all right? So that is basically what you'll observe in this case. The ratio of the mass of oxygen in hydrogen peroxide to the mass of oxygen in water, provided that the mass of the hydrogen is the same, would be a 2-to-1 ratio, all right? So what do we have here? Therefore, hydrogen peroxide has twice as much oxygen by mass as does hydrogen for the same mass of hydrogen. So therefore, you can actually see that in the formula, right? H2 here, the same, right? But you have one oxygen atom here, and you have two oxygen atoms there. So that's the reason why the mass of oxygen is twice that of the mass, I'm sorry, let me take that back. The mass of oxygen in hydrogen peroxide is twice the mass of the oxygen in the water. Okay, and here are some other examples. So let's look at this first pair of compounds. If you compare copper-1 chloride and copper-2 chloride, these are the formulas. Now, in the next chapter, we're going to learn about how to name these compounds. In fact, that chapter would be entirely dedicated to learning the rules for naming compounds, right? So you're going to learn why this is called copper-1 chloride and why this is called copper-2 chloride, right? But for now, we're just going to focus on the formulas and the percent compositions here, right? So in the case of copper-1 chloride, these are the percentages. In the case of copper-2 chloride, these are the percentages. And if you were to go into further detail and find out, okay, let's say you would figure out what the mass of copper is in a particular sample. In each of these cases, if they're the same, then what you'll find is that the ratio of chlorine in copper-2 chloride to copper-1 chloride is 2-to-1, all right? And we have some other examples here, which I won't get into, but basically, the percentages are different, even though the elements are the same for the different pairs of compounds. And that's because the compositions in terms of the different parts, in this case, carbon and hydrogen, in this case, carbon, hydrogen, and oxygen, they're different, and therefore that reflects in the different percentages in their percent composition values. Okay, so as promised, or as I stated earlier, the atom of any element can be further broken down into simpler parts. And just some general information here about a typical atom. Of course, as we can imagine, the atom is very small. And as I said before, you can break it down into smaller particles. These are called subatomic particles. And just to give you an idea as to how small we're talking about here for an atom, imagine that this dot has a diameter of 1 millimeter right across, right? You can actually fit 10 million hydrogen atoms across on that line from one side of the circle to the other for that dot, all right? So that gives you a picture as to how small a hydrogen atom is, all right? So just to give you some background, I won't go into any great detail. Of course, these particles people didn't just come up with these particles, they were actually discovered. A guy by the name of Sir William Crookes, he invented what is known as a Crookes tube, which basically, do I have a diagram here? Okay, so this is basically a replica of his invention here. It consists of an evacuated tube where one end is connected to an electricity source, which is negative. This here is connected to a positive source. And basically, it's an evacuated tube. And when you flip the switch, you see a stream of particles emanating from the negative end or the negative pole to the positive pole. And they're energetic enough to basically hit the walls of the tube right here. And it fluoresces. That's a term that they use to describe what happens when the negatively charged particles hit the wall of the tube. It basically lights up, all right? So, you know, the first thing that one could say about the particles is that they're negatively charged, right? And as always happens in science, when somebody comes up with a new discovery, then everybody tries to rush in and try to determine, okay, some other factors or some other functions that can be derived or discovered, right? So other people came in and played around with this and determined the nature of these particles. And the name given to these particles, they are called electrons, right? So the electrons that we now know to be electrons, that's how they were discovered, right? So as I said before, different people tried to figure out the nature of these particles. And the first one to have some success in doing so is a guy by the name of J.J. Thomson. And these were what he discovered in terms of the properties displayed by these particles. They travel in straight lines, they are negative in charge, and they're deflected by electric and magnetic fields, and they produce sharp shadows, and they're capable of moving a small paddle wheel. So what he did was that he recreated the same experiment with some modifications, which allows him to determine these properties, including putting a very small wheel, and he found out that the electrons are so energetic that they can turn the wheel, all right? So basically, that's what he discovered, that these particles have a negative charge, and they were called electrons. And there were other persons who came in and determined some other properties of the electrons. One person, for example, determined the actual charge on the electron. One person discovered the charge to mass ratio of the electron, and then another person discovered the charge on the electron. And therefore, if we know the mass to charge ratio, we know the charge of the electron, then we can determine the mass. So all those were discovered by different people at different times. And then the protons were discovered by a guy by the name of Goldstein. And basically, once he discovered the protons, then Thomson, J.J. Thomson, he also determined the protons and characteristics. And he also came up with the idea that, okay, so basically the atom itself is made up of protons and electrons, which is what the negative charges are known as today, right? So this contradicts, if you remember, the first assumption of the Dalton model, right? That the atoms are indivisible. It shows that they're actually smaller particles that exist within the atom. And up to this point in time, those particles were identified as the protons and the electrons. And then sometimes after, about 30 years after, an Englishman by the name of James Chadwick, he discovered a third particle. There was some mystery that took place between the discovery of the protons and electrons and the discovery of the neutron, because people realized that, okay, the protons and the electrons' total mass does not account for the total mass of the atom. There was some difference, right? And nobody could figure out what that difference was until James Chadwick came along and he discovered a third particle which allowed for the discovery of that, or explained that difference, all right? So those are the three fundamental particles that exist in the atom. Okay, now we discussed the periodic table earlier. I think I might stop after discussing this. Okay, so how did we get to the current version of the periodic table, right? Well, the first person who was credited with coming up with a periodic table is this guy here by the name of Dmitry Mendeleev. He was and probably still is the most famous Russian scientist. And what one account I've read about how he came about with his version of the periodic table was that he found out, and I think he was writing a textbook at the time concerning the different elements that were known at that time. He basically arranged the elements in order of their atomic masses, right? Back then, they didn't know anything about the structure of the atom, so terms like atomic numbers and so on were not known then. The only thing that was known about the different elements is that they have their own unique atomic masses. So he arranged the elements in their order of increasing atomic masses, and what he discovered just by looking at the trends is that after so many elements, their properties repeat, right? So what he decided to do was to construct a table where all the elements that have similar properties are placed in columns, right? He arranged them in rows, but when you get to the next element, which repeats the properties of the first element, you put that element under the first element, and then you continue, right? And basically, he came up with his version of the periodic table, which at the time had some gaps in it. And the reason why there are some gaps in it is because there were elements that were not discovered yet that would fill those gaps, right? One good example of that element would be germanium, right? So his version of the periodic table, do I have that version here? No, I don't have it. I saw something online. I thought I included it, but I'll probably post it in Canvas. In his version of the periodic table, the gap existed for germanium. And he was able to predict the properties of germanium, right? So much so that when germanium was actually discovered and they compared the properties that he predicted to what was discovered, there was a very close correlation, right? And he did that without even understanding the nature of the atom, how the electrons are arranged, which is what actually determined the properties. In any case, there are some unique numbers associated with each element. The first one we're going to talk about here is the atomic number. The atomic number, by definition, is the number of protons in the atom of an element, right? So each element has its own unique atomic number. So for example, sodium is the only element in the periodic table with atomic number 11, or phosphorus is the only element in the periodic table with atomic number 15, all right? Okay, okay, let me just do this page and then that's it for today. So another term that I need to introduce to you is the mass number, right? The mass number, by definition, is the sum of the number of protons and neutrons in the atom of an element, right? So please know the difference between the atomic number and the mass number. The mass number is the number of protons and neutrons, the sum total of protons and neutrons in an atom, while the atomic number is simply the number of protons in the nucleus of an atom of an element, right? So if you know the mass number and you know the atomic number, you can easily calculate the number of neutrons. That would be the mass number minus the number of minus the atomic number. And the symbols that are used conventionally for these would be A for the mass number and Z for the atomic number, right? And you can also represent a particular atom by using this symbolism right here, right? Where A is the mass number, which is written as a superscript to the left, and Z is the atomic number, which is a subscript to the left of the symbol of the element, which is represented by E. So for example, in this particular atom, the mass number is 35, the atomic number is 17, and therefore you can tell, based on that information alone, you can tell the number of protons, you can tell the mass number, and you can tell the number of neutrons by simply subtracting 17 from 35, which in this case would give 18, all right? Okay, so let me stop there. So let me make sure that the videos are published for, okay, so basically I've covered pretty much everything up to here. You may rewatch those topics and make sure you watch this last video right here, all right? And again, make sure that you submit assignment number 3 by Monday, all right? Okay, folks, so that's it. I'll see you guys next week. That's not bad.
Don't forget your bag.
Oh, okay, I think. Yeah, you too. Yes, sir.
Thank you.
Yes, sir. Give me just a minute.
Seriously? I want to ask you about how your test, because I couldn't find your syllabus. Is your test, is it like in your room, like on Fridays?
No, it will be in a testing center, right? I'm sorry?
So it's like all digital, it's like on.
No, you do a paper test.
Okay, and do you have any purpose tests? Like,
I could publish, let me see here. Let me see.
No, the tests are.
Okay, let's go down here. Let me check what this looks like. Past test keys.
And our first test is on the 3rd of February.
Yep, that's the schedule. All right, so let's see here. Just want to make sure this looks like something you can use. So this is the test answer key for test number 2. Oh, okay, that doesn't have, let me try this one. Hold on, this is weird. Let's see, check something out here. Okay, that's not it. See this one, test number 1. Oh, that's way back in 17. Okay, here we go. So yeah, you can use this to help you to review. So what I'm going to do is, okay. So what I'm going to do is, oh, it's already published.
Okay.
So let me take that out.
And like this test that we take like now, it's gonna be like same format and same type of question.
Yeah, pretty much. What am I doing?
I still show this weekend.
Take out this to avoid confusion. Yeah, take out this one. I might have some more I can publish, but for now.
We do it every. So not a hint.
Yeah, usually what I try to do is give a question per chapter. So like if we complete 3 chapters, then there are 3 questions and you do all of them.
Okay, thank you.
Yeah, no problem. Oh, let me also publish.
Yeah.
Oh. What's this? Okay. Yes, ma'am.
So I did the assignment
Okay.
on here. Am I allowed to just?
Yeah, you can just, right, you can just upload it. But make sure you do it as a PDF.
Yes, I
Alright.
can save it as PDF and send it.
Yes,
Okay,
ma'am.
perfect.
Mhm.
Thank you.
It literally said.
Ah.